Okay. So move the room around a bit. We think we have the audio from the remote people plugged into the speaker. May work. So I don't think it really helps the people online, but it should help us in the room. Let's see, and hopefully we can do this tomorrow. So this session we have some lightning talks. Hoping to be flooded by submissions. They haven't been. So there's not too many. So some of these are perhaps not going to be quite so lightning as less lightning. But we'll go in this order. Harvey is the only one who's not in the room. So hopefully Harvey, you can hear us and you'll go second after Mike and Wayne talk. By the end of the session, if anyone does feel an urge to offer a lightning talk, feel free to raise your hand. And hopefully everyone will remember the order because it's going to be simple. Screen sharing still working. Sweet. Okay. So I just thought we have a few new faces this year, so it might just be useful to introduce Combine, which is a computational modeling and biology network, of which CellML is one of the core standards. It's a website that's in the process of being transitioned to a new technology, so if anyone wants to put time into migrating websites, feel free to volunteer. But essentially Combine is a network to try and coordinate essentially the development of standards in computational modeling biology. So if you go to the website, you'll see we now have, should really know, but something between 7 to 9, say, core standards covering different aspects of modeling and biology, from the sort of CellML, SPML, synthetic systems biology type models, through to synthetic biology and some of the visualization of the different modeling standards. One of the reasons Combine started was to try and coordinate meetings. So we don't all have lots of meetings to go to all over the place. We try to coordinate them. And so now Combine organizes 2 meetings again. There's the Harmony hackathon on resources and modeling, something. Harmony, which happened a couple of weeks ago. There's a virtual meeting, and that's sort of a chance with not so many formal presentations, but it's more sort of breakout sessions, hacking on standards, and their supporting tools. And then normally later in here, there's a Combined forum, which is more a user outreach type event, so there's a lot more presentation. And typically now we have presentations in the morning and then hacking in the afternoon. I'll show a bit later where the next one is. There's also a bunch of things about trying to consolidate some publications, different mailing lists, how we sort of plug into the whole fair and fair sharing efforts happening around the world. So fair sharing is a good site to go to if you're looking to see what database or tool you might want to use for a particular purpose. And if you go there now, you'll see this computational modeling Combine collection, which currently has 8 records to view. So there's information about the standards in there, but it has information about a whole lot of things to do with data and other things, not just modeling. And just for a bit of history, you can see Combines started in 2010. And before that, you can sort of see the standards evolving on the left, various meetings happening around the world on the right. And if you look, back in 2009, in this very room was the last pre-Combine meeting, where we had a combined meeting for CellML, SVDN, Biofax, SPL, and MyAgic. So this is a very historic moment. So that shows sort of the number of meetings and how it's consolidated on this sort of combined but of course, we also have our own little workshops that keep going. They're much more focused. But if you are interested, there's an article there, and I can share the link later that talks about some of this history. So the other one is in, it has a whole bunch of mailing lists to try and give sort of central places to discuss various topics. One that was mentioned briefly this morning is the idea of an archive to share a piece of work. So it's combined archive. So there's a forum on that. There's a forum for the annotation, which is where all of the discussion should happen. That largely happens offline. So we try more and more to use this mailing list. And another one that may be of interest is this multicellular. So we are sort of reaching out beyond the scale of the one parameter models. There's a whole bunch, and there's always more getting added. You can go to the website and find them. And we also now have a Slack workspace, because that's much better than email. You probably need more information to be able to join it. So if you are interested, and all the standards are there, as well as the coordinators, just let me know and invite you to the workspace. It's very active, way active. Remember the time scale, 17 years for standing. So the next meeting is Combine 21, which is happening in October. It's not yet on the website, so we don't really know what it's going to be. But it's just going to be organized alongside the International Computational System Quality Conference in Connecticut, which at this point in time is scheduled as an in-person meeting in early October. And it'll depend whether that goes ahead, but it's quite likely there'll be some sort of virtual. So I think that's enough. That's combined. I don't know any more. I guess we have a bit of time. If there's any questions, feel free to shout out. In the meantime, I'll stop sharing. So Harley.
Yes, can you hear me?
Yep.
Okay, I just need to share my screen.
Any questions about combining or how this thing set up?
Can you see my screen now?
Yep.
Okay, let's just I might need to presentation mode. Okay, there's an update of our in silicon liver models over the last 3 or 4 years. So the liver modeling work here actually was originated from a large kind of a activity or project in Europe, which is called German Virtual Liver Network. That was a very huge project, cost about 20 million euros, something like that. And the project has a philosophy which is associated with multi-scale modeling or Physium or some other projects that to have in silicon models link the models from the whole organ level to the liver lobule, which is a construction unit of the liver, and the single cell hepatocytes, and as to proteins. That is a an article which was written about 10 years ago, which is starting of the project. So over the years, I think over the time frame of the projects, there are all sorts of works done, but I will bring to your attention the pharmacokinetics aspect of this project, because the pharmacokinetics actually is very nice annotation of the idea of multi-scale modeling. As you can see from, for example, from the critical side, that is a drug, and how we can use in silicon models to test whether drugs or a group of drugs or drug cocktail is helpful for combating diseases. In this case, as you can see, there are a few drugs which is uptake into the hepatocytes by its membrane, where the transporters get metabolized and get cleared. So this whole process works from the cell level, cell membrane level, and also protein level. And that was from an image from this same group 4 years later. Put into a big picture, somewhere in the middle, you can see the PBPK model, where you have the drug concentrations in different organs and tissues predicted, and with critical data to support the PK model, and using the PK model to make predictions for different patients, different gender, age groups, different underlying diseases. This, of course, is very relevant to the current COVID-19 situation we are in. And indeed, this systems pharmacology philosophy has been very powerful in testing the new drugs being used for COVID-19. And to plug in the organ level models, for example, this PBPK model require information of the blood flow to these different organs. Of course, this information can be obtained from imaging and ultrasound, MRI, etc. And of course, there are all sorts of protein level, gene level information need to be brought into the picture, right? Now, this is a big picture, so of course that is other people's work. So how about our own work in Auckland? I'll give you a few snapshots. We look into a specific commonly used drug called panadol. I think Sherry will give you a few more details after a few minutes. And so we at first have critical data. This data is very sparse. It's from neonates, a newborn baby, and it's from the Children's Hospital of Philadelphia. And from this model, we actually we were able to predict the PK profiles of panadol in very young babies. Can you believe that even young babies receive panadol through IV injection? And through the model, we were able to get the main picture of the metabolism difference between young baby and adults, which is clearly visible from the data. That is from the PK data model. And we also had a model which is associated with the heterogeneity of the metabolism distribution across the sinusoids, which is a capillaries in the livers. And this master model involves both PDE and ODE, so that is a intracellular model embedded into the van Animal model. So this is probably can be grouped into the protein level of models. And of course, we also have the model for the blood flow in the liver organ. So you can have a picture that from the population data, have the model prediction, have the model for the protein level of mechanism and to the whole organ. Publication-wise, I think is probably 6 papers published associated with these models. I want to thank the people who I get help from, and of course ABI, where all this research are rooted in. Thank you. Are there any questions?
Thanks, David. Any questions? Thanks, Harvey.
Okay.
Okay. Hopefully these are the right slides. Let's see. So another one that I thought might just be good to remind people exists is the Center for Reproducible Biomedical Modeling. So we'll just very quickly introduce that and what we're trying to achieve. And really it's this idea that everyone's seen in the literature, lots of things about how experimental work is not reproducible or not easily reproducible. But the thought that for computational experiments, it should be much easier. With all this software, should be easy to reproduce things, and there's various ways you can measure it. But what you find when you look, so we have biomodels with the large SML repository, we've got PMR with hundreds of CellML models, and what we find, of course, is that things are not reproducible. We've known this for a long time, and things didn't seem to be getting any better. But lots of the pieces for making things better, making things more reproducible, easier to share and all that, these pieces have been developed over many years now, they've been around for a long time, but people aren't using them. Why aren't they using them, and how can we help encourage people to use them? Essentially, that's where the center comes in. How can we develop tools and technologies and methods to encourage better practice in computational modeling, funded through NIH as a focus on biomedical modeling, but really it applies across the board. And essentially, it's a team with 5 of us, sort of based around the place. Herbert Zaro is the PI of the center based in Washington. And so he's leading the overall efforts. Jonathan Carr at Mount Sinai in New York is really sort of pushing the, how do you reproducibly construct the model? So if you have some data and you want to build a model from the data, how do you do that in a way that you can describe and share that with someone so that someone else can build the same model, or at least a comparable model from the same data? John Gennari, also in Washington, Seattle, is working on the semantics and this sort of real getting into the annotations that we should use to describe the whole modeling and simulation process, so that everyone can understand things. And Jan Moraru in Connecticut is leading the efforts in sort of how do you reproducibly simulate models. Everything we do from parameter estimation through to model building and running simulations. How do you do that in a way that's reproducible? You can share it with others, and potentially, if you want to look, for models or models that exhibit certain characteristics, how do you find that when the thing you want to search over is the output of models rather than the models themselves? And then in Auckland, we're sort of leading this curation service, working with journals that I'll talk more about this afternoon. And that's really how do we encourage or try to get the journals themselves to change the way they publish models or the way they review and publish models to then put pressure on authors to do their work properly. It's really what we're trying to do. And I think that's pretty much it. We'll talk more, as I said, about this curation this afternoon. There's more information on our website there if anyone interested.
Can you just remind me what the funding situation is with the centre? When do you go for a renewal? How long does it currently last? You anticipate the renewal cycle?
Yes, so yeah, it's initially a 5-year project, and we're in, I say, year 4, maybe year 3. But we're going for a renewal in September for a further 5 years. These P41 centres are typically at most renewed 3 times with 5-year cycles. So that's what we're hoping for. Yeah, September is the big one to try and demonstrate that we've done something. Questions? When is the schedule? Alarm's next. Sweet.
Yeah, sounds good.
Did you write sorry, microphone? See if it works.
Quickly going to talk about OpenCOR and leave OpenCOR. What if you already know about OpenCOR? So for those who don't, it's a modeling environment which is used to organize, edit, simulate, and analyze CellML files. And it is a cross-platform application with both on Windows, Linux, and Mac. It is a plugin-based application. And it works both on the command line as well as the graphical user interface. It has full CellML support. So we are quite for those who are not familiar with CellML, you is going to mention a bit more about that tomorrow. But yeah, at this point we have full CellML support, as well as partial CellML support, and I will explain a bit more about suits to standards for those who are not familiar with it. It is an open source project, and it is currently released under the GPL version 3 license. And it has a very simple website, openCOR.ws. For those who don't know, WS is for West Samoa, but .com, .org, .net, etc. were only used. So as a part of the WS website. And it is also on GitHub. As I said, it's open source. So everything is available on GitHub under the OpenCOR organization, and that's the OpenCOR repository. There are very few prerequisites for people who are interested in contributing to OpenCOR. So if you want, for instance, to create, as I said, everything is a plugin in OpenCOR. So if you wanted to create a new solver for OpenCOR, you could do that by creating a new plugin. And all you need for this is just Git, which most developers nowadays, CMake or C++ to change. The big one is Qt, which is a framework we use for the graphical side of OpenCOR. And then there are a few optional packages that you may want to install to speed up things if you want, for instance. So you just need those ones. OpenCOR has a lot of dependencies, but all of those are properly taken care of for you, so you don't have to worry about any of them. Now, the way it works is that typically when you have a model which is published, you will usually have the model equations like this, as well as some figures that demonstrate different aspects of your model. Now, that is purely paper-based. So obviously we want to have some standard that will allow you to make sense of those from the pure computer perspective. So when it comes to the model description itself, we use CellML to encode the model. So it is an XML-based format which is used to encode all the biological aspects of the model, and the mathematics is encoded using Matplotlib. Then when it comes to the figures, basically what we are doing here by publishing figures, we are basically running a simulation and then plotting or whatever the simulation results and publishing that. So in that context, we have another standard, which is CellML, so simulation, experiment, description, markup language. This is yet another XML-based format, which we use in conjunction with CellML to basically run models in a reproducible manner. And all of those, so both CellML files and CellML files, are stored on Tomic's visual model repository. And both of the standards, as well as the visual model repository, are accessible in some way or usable through OpenCOR. So I'm not going to demonstrate anything, but this is a lightning short, but yeah. So we can interact with both CellML and CellML within OpenCOR, as well as access the visual model repository. Also, more recently, well, over the past 2 or 3 years, we have created, thanks to AB rules, we have Python support within OpenCOR. So, which means that you can use OpenCOR from a Python prompt as well as a Jupyter notebook, etc. And it all works very nicely, but as we will see in a minute, there are some limitations which I'm going to explain the direction in which we're going very soon. And because everything is plugin based in OpenCOR, it means that we can interact with OpenCV Sync. Actually, that interaction already exists. It's just not officially part of OpenCOR. And we can also potentially interact with OpenCV Sign. Now, as I said, we have Python support in OpenCOR. And the original reason we did it the way we did it is that we wanted our Python support to allow us to interact with the graphical user interface. So for instance, the idea was to be able to create plugins using Python. And in order to do that, it meant that Python support had to be done through Python Qt, which is another package which allows us to access Qt from Python, from a C++ program. Now, what that meant also is that when we want to ship OpenCOR with Python support, then we have to ship Python itself. And in the same way, while if we have to ship Python itself, we also want to ship it with some very useful packages that most people use, such as Matplotlib, NumPy, SciPy, etc. Now, the big downside of this particular aspect is that whenever there is a new version of Python, then technically speaking, that means that we need to generate a new version of OpenCOR. So right now we are in version 3.9 of Python, when the version that comes with OpenCOR is version 3.7.5, if I remember correctly. So that's the downside. The other downside is that whenever there is a new version of OpenCOR, all the other packages that you may have installed within OpenCOR's Python environment, well, you will have to reinstall them, etc. And the other thing is that if you just want to have a Python script where you just do import OpenCOR, well, you can do it, it works, but you have to do that, obviously, from within the Python version that is shipped with OpenCOR. So, to cut the long story short, it's not very convenient. And the other thing is that at the end of the day, from feedback that we have received, people are not so much interested in using Python to control the GUI. What they want is just, typically they will have a model, they just want to run simulation from a Python script and that kind of thing. And they just want to take advantage of OpenCOR to read, say, the CellML file, run a simulation, and that's it. So for that reason, we have decided to kind of create libopencor. So libopencor is going to be a pure C++ library, and a C++ library that is going to support all the core features of OpenCOR. So basically, pretty much everything that is in OpenCOR except the GUI, graphical user interface. That's very good. It's going to take advantage of libCellML, which Hugh is going to talk about tomorrow, which means that it's going to support CellML 2.0. So some of you may not know, but there is currently CellML 1.0, 1.1, so that is not going to be supported directly. but there is going to be a way to convert a CellML 1.0 1.1 model to CellML 2.0 automatically for you. So there is no point there. So OpenCOR going to support libCellML. And in the same way that libCellML has different bindings, so libCellML is also a C++ library, but because we also use technologies such as Swig and Mscripton, it means that we can generate bindings for libCellML. And at this point, we have Python bindings and JavaScript bindings. So those technologies are going to be used with libopencor as well, which means that at the bottom, at the end of the day, we'll have a C++ library, but you will also easily be able to use libopencor from Python as well as JavaScript. And that's, I think, kind of that for me. So if you have any questions.
Once I was trying to import BoneGraph tools library when I was using OpenCOR in Python, but I couldn't. So it couldn't just add the whole BoneGraph tools library. What could be the problem?
That's pretty much next to impossible to tell. So knowing exactly what you are trying to do exactly. So what I kind of suggest and offer is that next time we are at the API, you show me exactly what you try to do. And I'm pretty confident that should be able to do pretty quickly what the parameters.
Thanks.
Yeah.
So, your ability to remove the use of Python as a package within OpenCOR is because you've got the CellML, the OpenCOR library. That means you can link through script to Python. Essentially, it's because of the OpenCOR that enables you to do that.
Yeah. So I mean, on many occasions, so David mentioned the combine effort, etc. So at harmony, combine, etc. People have said, "Oh, we would like to be able to use CellML." But the way we provide Python support in OpenCOR, it's not convenient at all for them. They said, "Oh, if we could just go," so you may know about SciPy, which is the repository where you have all those Python packages. So they said, "Yeah, if we could just pip install OpenCOR and then from their script import OpenCOR, then that's what they want. They don't want to have to install all of OpenCOR and then use a Python environment that is shipped with OpenCOR." But to be honest, I've had to do that myself for some work, and I find it to be very cumbersome to use, very kind of constrained. And I wish I was just able to do import OpenCOR.
And so the idea of having lib OpenCOR would then allow finding symbolism, so then we can
So
actually do
basically, what we have with libCellML, I mean, I'm not going to reinvent the wheel. I mean, what we have done with libCellML works perfectly fine. We have a C++ library that people can use directly. And because we have the Python bindings, we can use libCellML from Python. So I want to do the same. And also, Hugh has created a JavaScript binding using Mscripton, which means that basically you can use libCellML from a website, from Node.js, etc. So again, that's something that I want to do with the OpenCOR. That's it. Not going to reinvent the wheel. Everything works perfectly fine with libCellML. So just kind of mimic, except that it's going to be for all the features, core features of OpenCOR. And that means that the combined community at large will be able to take advantage of CellML without having to worry about the GUI size that comes with OpenCOR. There is no question that the GUI, so OpenCOR itself, is still useful for people who want to create models. But a lot of people, all they want to use is to consume models. That's all. They are not interested in creating new models or whatever. I mean, clearly some people are interested in that. And those people will keep using OpenCOR because it's much easier to basically edit CellML files using an environment like OpenCOR rather than Notepad and editing the Matplotlib code or whatever. Even so, some people prefer that.
It's a question in the chat.
Also. Oh, Docker, yes, we have tried that. So we have created a Docker for OpenCOR. And it works okay, I suppose. It's just that ideally, we would fully take advantage of the CellML standard, so CellML simulation experiment description standard. Unfortunately, at this point in time, CellML support in OpenCOR is somewhat limited. And without going too much detail, our Docker doesn't take advantage of the CellML support. So what we do at this point is that we have the Docker for OpenCOR, which is actually on GitHub as well. And it is also on Docker Hub or something, I think it is called. So if you go to Docker Hub and do search for OpenCOR, you should find it normally. And that means that you can fire up OpenCOR and provide it with an input file, which is in JSON format. But basically, it would, you provide in that input file which CellML or CellML file you want to run, as well as the initial conditions from different model parameters. So it's kind of a quick way of using OpenCOR from a Docker. Maybe some more work will be done in that area. Depends on people's interest.
But yeah, it does show how you can package up a specific version of OpenCOR for a specific task with a certain set of Python scripts.
Yeah.
That works well.
How did the plugins work with the library? Or, do you use a very certain set of plugins for it, or is it still modular and does the OpenCOR provide the plugins through its API?
So that is, at this point I haven't finalized, I think, what the OpenCOR, because what is true, okay. If we go back to OpenCOR, as I said, everything is a plugin. So for instance, we have different servers, CBOD plugin for that, forwarder plugin for it. In libopencor, we will need to be able to run simulations from using libopencor only. Now, can we have some kind of plugin mechanism for libopencor? I don't know. I mean, because the other thing that I didn't mention that maybe very clearly, OpenCOR, C++, like libopencor, but OpenCOR is very heavily Qt based. libopencor, we want it to be purely C++. Now, when it comes to OpenCOR, because it is Qt based, it's very simple to handle and manage plugins. If it is purely C++, it means that we will have to find our own kind of plugin strategy. Maybe there are some C++ libraries that can be used for handling plugins. I don't know, but so yeah, it's still kind of undecided, to be honest. No, I mean, ideally, okay, let's leave that there. Ideally speaking, libopencor will also be plugin based. That's what I would like, as much as possible. Right? Whether technically speaking it's going to be possible or easy to do, that's another question. And the other thing also is that let's not forget that we also want to have Python binding, JavaScript, and also JavaScript binding. So depending on some of the technology that we may end up using from the C++ side, it may or not make it simple to have Python bindings. I know that, for instance, for libcnml, we wanted to take advantage of a C++ 17 feature, which is std.ini, and it was std.ini, is super useful, but you can't fully take advantage of it from the Python bindings. Anyway. So there are sometimes things that you have to keep in mind if you want to have binding. Otherwise, you may still end up getting the binding, but the bindings are going to be super difficult to use or unnecessarily complicated, and it's not going to end up. I'm not going to end up in something that is really Python. So
it is going to offer what people need most of the time initially. Right?
Sure. I mean, I think, as I said, within the community, people are interested in using CellML from fine. But not really supposed to drawback that come with our current Python support. That's what has refrained them from using CellML. At least that's what I've been told.
One last question from the praying mantis who's decided to join us. Wants to know when will the OpenCOR be ready?
Sorry.
The little praying mantis up here would like to know when the OpenCOR is going to be ready. Very eager to know.
If I was fully in charge of my workflow. Okay. I mean, let's be honest. I mean, LibOpenCOR has first been discussed. Okay, I'm not going to leave the timeline. I would
That was
have
2019.
I want it, to be honest. I really want it. So, and I think it's also fair to say that even with for Spark, at some point it could be very useful to have these OpenCOR also to OpenCOR itself. So hopefully, yeah, we will agree that even with Spark, some leadership.
We can count on the current Python and OpenCOR not disappearing too soon.
Correct. Yeah. I mean, that's for sure. We are definitely not going to remove the current Python support in OpenCOR for as long as LibOpenCOR is not about.
Cool. Thanks, Alana. So now we have Sherry who's going to tell us about pharmacokinetic modeling of panadol.
Good afternoon, I'm Sherry from Dr. Hartman's team, who is presenting the liver model previous. And I'm going to expand a little bit on the pharmacokinetic models using panadol as an example. So I guess most of you should have heard of it. So talking about AKP, there is just a recent review from the University of Sydney saying that it's not an effective in most pain conditions. But it has been widely used for many years and can lead to severe toxicity that overdose. There's plenty of clinical data for adults, but there's not much for women because of the ethical issues. So therefore, having a genetic model could be quite useful. So my research aimed to model the metabolism and the time concentration profile for AKP and its metabolites with the PK. So our model was adapted from a study from the University of Otago, who has introduced an adult model that simulates the plasma concentrations and also the urinary concentrations. So their models consist of 7 ordinary differential equations, one is shown here, which represents each step of the metabolism and also the expression. So of course, before our adaptation, we first need to reproduce the results, and we also simplify their models by replacing the metabolic kinetics, which is the Matthew's kinetics by ages and clearance. And while doing it in MATLAB, Harvey introduced CellML to me, so we also pop that in CellML, and we generate the result for a 60 milligrams per kilogram oral dose, starting from time 0, which is the time for administration, to 10 hours after dosing. So the circle we used was CVOD, and the time interval was about 1 month. And here is our CellML results compared with the clinical results. So they look pretty much the same. So we were happy to move on. Then we modify our model according to the available pediatric parameters and also estimated some by elementary scaling. And the model has the same ODE system as the adult one. And to validate our models, we compare our results with the observations from the Children's Hospital of Philadelphia. And we collected the concentrations from the neonates during the treatment of fever with an 12.5 milligrams per kilogram IV dose. And those of our CellML results and also the meta results are in line with these observations, which are the data points here. Yeah, we are now also working on different models for remdesivir, which is one of the proposed drug for COVID, and hopefully we can also contact design of once we start. And I've just started to use them, so I hope I can learn more about it. Thank you.
Questions for Sherry? How are you finding CellML so far?
It's showing it like quite useful when we were just trying to estimate the parameters because it has a better interface than that, so we can just change the numbers and it just automatically generates a graph without changing all the initial conditions because in MATLAB we might have to change the code to run the parameters. But I just started with this.
Are you building a single model or using import mechanisms for each of your imports for each of your mechanisms here?
Sorry, import from.
So when you build your CellML model,
Yeah.
are you writing it as one single model or are you
Yeah, a single one.
single model?
Yeah, for this one, that's just the single one. But if we combine our models, that may be.
Any other questions? Excellent. Cool. Thanks, Sherry. So now we have Hugh, who's going to tell us all about libCellML. I assume.
So this is going to be a lightning talk, but Alan Garni is sort of taking my lightning, so I think I'm more of a thunder talk. It's going to be a co-medicines of a thunder plus talk. So we're here for the CellML workshop. A lot of what CellML is defined in the CellML 2 specification now. That has recently been published in CellML timelines. So what we want from CellML is what we know it's an XML format for exchanging models, and writing directly in CellML is not very useful, or indeed a way I think anybody should write the models directly in XML. Sorry. So to help you write your models in CellML, we have been working on a C++ library, libCellML. And it takes away the idea that there's any XML going on, if that's just an exchange format. And it's really looking at the objects in CellML, the models, the components, the units that your variables use in your components, and the math that exists in your components. So it's really looking at using those objects and trying to make life much easier to manipulate and manage a model. So, so what have we done so far in libCellML? Well, we've done the basics. We're able to create and manipulate your models, print and parse them from files. That's a good start. We've been doing this for a while now. But just recently, we've added in the creation of binaries and C++ binaries. And now we've got some Python binaries, which I'm trying to get up onto Pippy, so we can just do the pip install with CellML, which is nice and easy. And everyone can use it in Python, which will make it really easy to get hold of. And in the very recent past, we've added JavaScript, so you can now run libCellML applications in the browser or using something like that. So that is something that is, I think, really useful. And we'll see a little bit of that tomorrow because I am currently doing a tutorial on how we can use libCellML and some of its uses. Hopefully we'll see some of that in action tomorrow. One of the big things that we have for libCellML is it will allow you to validate your model against the specification. So it will tell you any violations of the rules of the specification in the model. There's quite a lot of rules, and it's quite useful for making sure that you can then go on further to say generate some code for that model. So if you don't have a valid model, the code generation is either not going to work or it's not going to give you something you can actually simulate. One of the things that we want to do is the modularity of our models. So we want to put our units and have separated parameters from our components. And that means using imports. libCellML only supports local imports. That means from the file. We're not capable yet of just getting an import from somewhere on the web. It's something we have decided to put in the too hard basket for now. As long as we think if we can support local imports, then that at least allows us to show best practice and use modularity to build our models. One of the recent additions to the code base is analyzing models, doing some model analysis. So outside of the validation, we can look at the mass and decide, for instance, if your units are consistent across your equation. This is useful. A lot of people write their equations dimensionless, so they have to weigh their units, but that's sort of not very useful. It's much more useful to use the actual units as they're supposed to be in making sure it's all consistent so that the model makes sense. And we can now generate quite easily schedule code for Python and C. It is possible to write your own generator, so you could, it's feasibly possible that you could write, you could make your own generator profile that would generate code for whatever language you chose. But possibly it would be easier to ask us to do it for you. Put an issue on the code on the website and say, I need to be able to generate code for such a language. But I think Python and C will cover the vast majority of people. What we haven't done, well, this list is amazingly short. We've really cut it back recently. So one of the things we want to do before we really release CellML 1.0 is to handle DAEs in our code generation. This is something we're not quite able to do. We need to be able to manipulate our equations and rearrange them so we can solve them. And one of the new things that CellML 2.0 brought to the CellML community was resets. So we can do model things like cell division and things like that. And so we currently don't generate code for any resets. So if you model a reset, if you have a reset in your model, the code generation will quite happily ignore that, which is unfortunate. It's something we want. So two things we have to do to really say we're ready to release CellML 1.0, and we're getting on with the DAEs, handling DAEs, and we're going to release that as 0.9. And then hopefully once we get the code generation for resets done, we will have 1.0 available. One other thing we've been working on is the libCellML website. A lot of the work there's not really much point in sharing a library like this if you can't get the documentation. It's not good. Can I see the API for these objects and these classes? How do I use it? What information can I find about it? And can I get some tutorials on it? So this is what our website has got the information for, downloading binaries and all the information surrounding CellML as well. I will actually just take a quick peek at that in a minute, I think. And the website is also offering some services. So most of you in this room will be writing models in CellML 1.1 or 1.0, whereas libCellML only works with CellML 2.0 models. So we have on the website a service that will translate your CellML 1.1 models into CellML 2, so you can get using CellML code. What doesn't the website have? It doesn't have the downloads and releases just yet. Still a work in progress. I have got binaries in one place and I've got a website in another, but I haven't yet joined up the website telling me here are your downloads you can offer people to download. We do get some around the place. So I will just quickly show you the website. I will stop sharing. The website's at libcellml.org. There's an update that's going to come in tonight, so it's going to change a little bit, just the time a little bit for tomorrow. When we get to tuck into the libcellml tutorial, which I'm sure you're very excited to see. I'm very excited to see tomorrow. So here we have the homepage, obviously the downloads. As I said before, there's no downloads there. I can't download links on those ones. But we do have a good chunk of documentation and the service for translating the CellML models. So I can, if I want to translate a CellML model, I could upload one of these OBX data files or just a simple CellML model. I could open it up, and then I can translate it, and I can download it, and there will be CellML 2.0 versions of my 1.1, 1.0. That's quite useful in itself, and that is just using using SSLT just to transform that model. So there are a few little quirks that may not work for every single model. For most of the ones we tested before so far. The documentation is one of the key things I think everybody needs to be able to get access to. So we have this API documentation, and in here you can run around and you can see all the documentation that we have for our code, and it should be fairly comprehensive. We should have everything in the API documented here and available, and we have different versions available. If you want to go to the older versions, you can do that as well. And we also have some user guides where we have a bunch of tutorials that you can go to, and they're all there, and we have a lot of content there for anybody who wants to investigate CellML, and hopefully tomorrow we will have some binaries and we can hit install. We can go through a tutorial and see how good libCellML is. Oh, one more thing. If you want to get your fancy picture up here, all these people here have contributed to the code base with the tutorials or libCellML itself. You can join in and make some changes and contribute to the project, and your name and picture will also appear here on the list of contributors. So it's something to aspire to. I'd like to thank obviously our supporters over the years. We've had a number of them and realised that we can get this project as far as it is now, and I think we're getting very close now to having a very usable product. Any questions?
Questions with you?
How are you finding update?
We've got a few people who are trying to use it at the moment, but it's just they want to be able to just install and use it in Python. And you can do that if you know where to look right now. Tonight, I'm hopefully going to make it more widely available, but we're sort of targeting because it's C++ background, we have to make a very particular version of Python. So we're targeting sort of 3.8, 3.9 sort of versions of Python for different operating systems. So we're trying to cover the majority of bases. We won't cover everybody, every variant of Python. We just don't have the resources for that. But we can create it's kind of a seamless product. We make use of a lot of the GitHub actions to generate our binaries and splash around the world. So it's not too hard for us if we have a particular need for something we don't currently have. We can add things, but for the way we're just trying to adapt it to the 89% there's a few interesting things when you start doing things like JavaScript and then scripting, building everything within scripting. It's not quite as straightforward as what we might think. Things that isn't straightforward, we need to be making changes.
Any other questions? I'll move my laptop again without breaking it. Okay. So amazingly, we are starting to run out of time, and we need to make sure we're doing this long enough. So this is going to be very likely.
Here's some slides that from someone. Luckily, they have my name on it, so I think I'm going to use some. But essentially, this is just a quick update on where we're at in terms of the sort of standardizing annotations. We're combining some of the tools, libraries, and so on with quality. So essentially, in this context, when we talk about semantic annotation, it's really how do we add biological knowledge to our model descriptions? How do we add that knowledge biology? You see with CellML, where we're just pure maths, we have no biology in the models at all, so we keep this a lot. In SPML, there's a bit of biology in the model encoding, but not everything, and nothing standardized. So how do you search for a model where you're trying to search in different types of models, different repositories? How do you bring it all together so you can just go to one place and search and know that you'll find any relevant model? And once you find it, how do you understand it? And even more importantly, we talked a bit about this morning, how do we then integrate these models and compose them together? We need to be able to understand them. And of course, this all ties in with making models better. So the thing that's new, almost brand new and still changing daily, is we have a new library. So we've had a specification for a while on how you should annotate, but it's still hard to do. So what we're trying to do with Libomics Meta, which is being developed under the Center for Reproducible Biomedical Modeling, is to make a library that is aimed at software developers like Alarm, integrating this into OpenCOR so that you as a modeler can annotate the model as you go. That's the easiest and best time to capture knowledge. But then because there's a whole bunch of people that like to hack, it's always good to have Python as well. So just like with libCellML, there's been a big effort to make the Python bindings to the C++ library work very well. And if there's time tomorrow, we can go through a tutorial on how to use it. So essentially, this is the idea where you want to make it possible for those applications in C and C++ to use the library directly, and other packages such as Tellurium, which is a Python-based SVML tool, can use the Python bindings. So that gives us a library, so we can start trying to make annotations and do it consistently, regardless of your model format and other things, and then store them in the same way. When you do that, you then want to start looking at, well, what is a good annotation? I mean, how do you measure good annotation? And it's hard. So in a random meeting once, we came up with a bunch of C's, to get a bit less obvious as you go down the list. But essentially, you can look at things like completeness. What percentage of a model or things in a model that should be annotated are annotated? Are there conflicts between annotations? Do you annotate a chemical species with an anatomy term and things like that? And then, are they correct? Which is also hard to know. And then concreteness, which is a bit of a stretch. But really, how specific are the annotation? Is it like such a high level of abstraction that it's not useful, or is it a more useful level of granularity? So those are sorts of things you can start to look at across repositories and across models to see what are good, useful annotations and how should we encourage people to use the library to produce annotation. So just as an example, if you look in biomodels, they have these curated models, something like 1,000 models that have been curated by people to say that they're good models. Those curators have done some annotation, or perhaps even the people who created the models annotated them. So of the 30,000 reactions in biomodels, curated models, you can see, first of all, that there's a third of them have no annotations at all, right? Just pure reactions in SQL. Then you can see another third that are being annotated with the gene ontology. So those are probably reasonable. That's a reasonable ontology to use to annotate reactions. But then you can see this 1,300 reactions have been annotated with SPO, the system quality ontology, which is perhaps less useful, but potentially still valid, but not so useful. But then you also have this other one that have other annotations that are just a real mix. So you can see if you were trying to search for reactions across all models, and your search tool would normally use something like the gene ontology to guide you to help search, but that's not going to find all these other reactions. So if we can get people to standardize and do things properly, it makes it much easier to find. And that's it. That's where we're at. With that, that was my part for Richard.
Okay, are you considering annotating the physics of the models?
It's a good question. And yes, to some extent. So definitely the omics metadata spec and the library, we're always using the ontology for physics and biology to make the composite annotations. But I don't think it's going into the level to describe the physics properly.
Just seems to me there's an opportunity to do with what 2 years ago. Build in elements can be using this for annotating models like the core, then we should really be talking about the and checking the physics, because line graphs clearly gives you a much easier way of dealing with the physical end.
Yeah, so you can definitely do things, describe flow potential and that sort of thing. It's just not routine done. The software is definitely there. Other questions? No. Now we'll move on to Richard. We will hopefully finish before the end of the afternoon.
Sorry, I'll just put that window up on the right screen.
Okay, I won't do like demo straight up, but if it comes up in the questions afterwards, I've got some things I could share. Just, so I'm Richard, nice to meet you. Sorry.
It says when you know it's time for a new laptop, we're plugging in your power reset your adapter thingy.
Right. Fantastic. Yeah, so I'm Richard, for those of you who don't know me, and I just wanted to give an update on some nifty stuff we've been doing in the OpenCOR library for calculating general derivatives and using it to do faster computation than we've been doing before. So I'll just okay, so first an intro to what the Zinc library does. It's a library for representing finite element models. So we take the body and divide it up into these finite elements, and we describe field quantities over it. So we interpolate in those boxes that we see over here, parameters to represent, say, the geometric field coordinates or any other material or solution field that we care to do. And one of the features of the Zinc library is it supports higher order basis functions, that's like qubit functions, and also more recently general linear maps, so you can do some quite clever interpolations of parameters. But in addition to the finite element constructs, it's got a rich set of other operators that you can take the field quantities that you have from your model, do further maths on them, and then create derived field quantities on it. And one of the things that I worked on at the start of this year is to have a very general way of evaluating derivatives out of these, which I'll explain as we go. But the Zinc library is also for making 3D graphics visualizations. So you can take those quantities that you derive from your model, and then you can use them to control and orient graphics on your screen and make very rich visualizations. But it also has some utilities built in, so nonlinear optimization is something that we've been doing, but in general sort of manipulation of the model. But that's about where we say that the boundaries of the Zinc library is. And that there's some information there about, sorry, I just did that one, about, it's written in C++, Windows, Mac, Linux, and with a C++ and Python API. And like Q said before, very soon you'll be able to just go pip install openCMS.zip and get your hands on it, or use one of the other tools such as Matplotlib that Hugh writes, which will draw it in for you. These are the list of operators that can take the quantities that you have on your model and do further math on it. Quite a lot of them will just do things like, so you can do arithmetic things, you can add and multiply, you can do sines and cos and all that sort of math. But there's also things that do integration and summation over your whole model. So you can write some quite complex equations with it, and all the derivative functions, such as so a very rich set of functions are available there. And I've highlighted the final element one because that was where it all started. It was just initially you could interpolate over these final elements, and there's a whole lot of machinery and classes behind the scenes that supports that. So it's a very big part of it. But over the years, the ability to make general mathematical expressions has been a very strong part of Zinc library. But Zinc was originally developed in the application CMGUI, and there's still, that some of you will use, and there's still a handful of functions that are not yet put into the Zinc public API, but they are hidden inside it. And usually that's because no one's asked for it, or they're just a little bit not in the form ready to make public, because when we make an API on Zinc, we intend to support it pretty much indefinitely. And so far we haven't really had any breaks in our library in 8 years. And I think that's one of the features that makes people want to continue to use the library. So the first thing that we, first reason we put this general field operator expression language in, but was just to help visualize things more than just the fields that you read in, with your model. In this case, we have a pointing at the deformed coordinates of a model, which have got those blobs in the corner of it, and big X is the undeformed coordinates. So large strains are defined, well, the Rodian strains can be defined by this equation here. And we would define it in Zinc by making the gradient of deformed with undeformed, subtracting the constant of the identity matrix, and then multiplying by the constant half. And from that, we can do an eigenvector, eigenvalue and eigenvector. And those are the things we're after, because we want to orient the those little arrows to visualize the strains. So that's the concept of Zinc as a visualization engine, is that you take the values you have and you write exact math expressions, and then you use it to control your graphics. And we can do funky things with coloring and changing arrows to point inwards for compression and so on. So next, since we had this language for defining expressions, it got a bit bigger than that. We wanted to do things where we summed over sets of points and things where we did integrations. And that led us naturally to doing things like least squares fitting. So we do least squares fitting to take one of these geometric models and fit it to the data to make a personalized model for a patient, or fitting a specimen, a rat, say, in an experiment, so that we can have a geometry that's customized to that individual. And this is literally the expression that we use to do least squares fitting. The part on the left over here is why I don't like using touchpads. So this bit here is the sum of over all these data points on the outside here, where we are projecting them onto the outside of the model, and we're trying to fit it so that we make those little bars as short as possible. We're trying to pull out that figure 8 shaped thing, and that's intended to be a simple kind of heart that has 2 chambers, just to give a demonstration without being too expensive. And on the right is the solution here, but it wouldn't do that, it wouldn't stay in that shape without some other conditions. And in the second half of here, I've got these smoothing terms where we have the gradient of the field with respect to physical coordinates, and the gradient of the gradient. And they control essentially the strain the compliance is strain and the curvature of the body as you fit it. And what that means is that we can fit the outer surface of this, but at the same time, keep it in that figure 8 shape and do the right thing by it. But this equation does not show you the summation of all those terms. I is like the number of geometric coordinates in this case, or the number of components of the dependent field, and J and K are essentially the dimensions of the elements that you have there. I could demonstrate that later if you're interested. So when we solve this one, we use the Newton iterations, and they essentially, to do that, we need essentially the second derivative of this expression with respect to the element parameters. So that makes a big matrix, and in each iteration we need a force vector which shows the error of fitting that we're targeting, and we aim to find the minimum where the set of parameters for your field that give a zero slope. And so this is the task that the optimization has to undergo. Just so in order to do this, there's a whole lot of derivative evaluations that we have to do internally. And so in this year, I've generalized the derivative evaluation so that you can not only get derivatives with respect to the inherent coordinates, this sort of unit box that represents the internal space of each element, but you can also ask for derivatives with respect to the parameters of a field in an element. One of the interesting things about the implementation is that I always do it in the order as specified. So you can only ask for derivatives with respect to parameters after the derivatives with respect to xi. Otherwise, you get some rather interesting combinations and permutations of things. But that's usually how you need to do it, because if you have a derivative expression in your maths, pretty much the last thing that you're going to do is do the derivatives with respect to parameters that we need here. And so I told you about all the operators that we use to make all the expressions, and we use essentially what's called automatic, evaluate automatic derivatives of those operators. And this should give you an idea of what's going on inside Zinc when you are doing these calculations. So down the vertical axis are the fields that you're evaluating. So every single term in your expression is a separate quantity that has its own set of values. But each one of those is defined by one operator that does its expression in terms of the previous field. So looking at the very top here, see if I can use this one without moving the slide. At the very top of it is the field that we're trying to solve for, which is a finite element, an interpolated field. And finite element fields are, you can get any order of derivative with respect to the elements, but in terms of parameters, they're always linear with parameters in conventional finite elements. So the second derivative is always zero, which is what I've shown at the very top. That's it on that. And so I'm just showing the part of it where we're doing the difference of the projected coordinates and the coordinates for the data points. So this UD is the coordinates of your data. It doesn't vary with anything, so it's got zero derivatives. You subtract one from the other, and therefore you inherit the derivatives of one of those. Addition and subtraction are trivial for getting automatic derivatives for, but multiplication is not so trivial, because you'll see in here that there is now a second order derivative with respect to parameters, because the product of the first derivative of the two terms, which are itself add in there. But in general, if you have n derivatives of the source fields, there end up to be quite a large number of permutations of higher derivatives. And remember, these are also multivariable. So there's a lot of indexing of values in there, but it's actually something that anyone who's skilled in mathematics could implement the code into. So just at the bottom, you'll see that, so for each of those operators that we apply there, the derivatives are either 0 or trivial, or we use some multivariable product quotient or chain rules to evaluate the derivative in terms of the values and derivatives of the fields they depend on. But we also have the ability to fall back to a finite difference approximation. So derivative is the rate of change of the field with the rate of change, with the change of the quantity that you're varying it over. So that delta over delta. Just a second. Now the last two values there are essentially the things that we want to get out of this. The first red tick there is the force vector, which is on the right-hand side of our matrix equation, and the last one there is essentially the matrix itself, so the Hessian. And so through the API of Zinc, you can write the equation and then go in one step and essentially ask for element stiffness matrices and force vectors. And so you've actually eliminated the need to derive the mathematics for element stiffness matrices yourself. And that is the main power of what's been going on here. So I'll just cut through to the results here. So we need to do this in anger because we're fitting whole organ models to data. And we had a problem that they were taking 2 hours per iteration with the previous black box non-linear optimizers that we're using. And that figure 8 that I showed you before was a bit misleading because the new method and the old method were maybe only, 5 times difference in speed, but with bigger models, it actually got much worse. And so now we've cut down things that took 2 hours to solve to under a minute, and that's a massive improvement for the people doing the work there. But not only that, this approach is able to be run in parallel with some further development, because there's always a bit of code that's not going to be thread safe and so on. So there's a potential to speed up the matrix assembly by the number of cores on your computer. There's scope to use this approach for other optimizations and solving PDUs. But as I said before, you have to implement all of the derivative terms with the exact mathematics. If it falls back to that numerical finite difference calculation, it gets quite slow again, but it is precise, so it will get the solution. So it's actually quite useful for prototyping, but for performance, you need to put the right maths in there. But I think it's this approach is less error prone than hand-coded element stiffness matrices that are commonly used for quite element formulations. So just wanted to put a plug in for the people who've been putting effort into OpenCOR Zinc over the years. So Alan and Hugh who are here, and many past contributors, David and Aram have also got code into it. So there's a number of people who do it. It's all open source and free. The website is openCMS.org. And also thank you to the NIH Spark grant, which has been funding our work for the last few years, and of course Peter for managing that sort of thing. So anyway, thank you very much. If you have any questions.
I was just thinking, imagine getting 100-fold, what it would cost to get 100-fold improvement in speed to something like faster hardware.
Yeah.
It's software, it's algorithmic improvements that make a huge difference.
I agree, and I think not enough people invest the time to profile their code and see what's actually working. And there's massive gains to be made. There's power stations that don't need to be built if you do it right. And it is more complex to do multi-threaded parallel coding. And I know that's the way processes are going, but if you can get, 100 times speed up out of the serial improvement, the fact that you've got 6 cores is kind of a little irrelevant. But there's another 6 to 12 to get out of your computer. The only thing is that the noise it makes when it's doing these on my laptop, I think it might have to have liquid cooling if I actually ran it with all the cores for an extended period of time. So there's still a need to have servers and cool rooms doing the big math. Oh, sorry.
Any other questions? Any last minute volunteers to give a lightning talk? No. Okay, thank you. Anyone who wants to see those demos, make sure you see them. Okay, so afternoon tea is just out here. Hopefully there might be more coffee this time around. But then we'll start again around 3:30ish. Thank you.
I'm going to be